Thank you for joining today. So far as part of this series, we've heard a little bit about the JWST observation reduction from Tom Williams and the production of these beautiful images, but also a little bit about the bubble populations from Liz Watkins. Today, I'd like to talk a little bit about one bubble in particular, and that is the phantom void. First of all, I'd like to tell you a little bit about the history of bubbles and why they're important. So bubbles in the ISM, both within the Milky Way and in nearby galaxies, have been studied since the early 80s, late 70s, so several decades now, in the atomic hydrogen, so that's the H1 21 centimeter line distribution across the Milky Way and the nearby galaxies. We can see several examples here where we can see large-scale holes of the order tens and even hundreds to even kiloparsec size within these galaxies. So these are large-scale features within galaxies, very important for understanding the large-scale structure of galaxies, akin to, for example, spiral bars, spiral arms, and even galaxy centers. These really do constitute an important part of the structure of galaxies here, and we can see that. So some really nice, beautiful VLA observations here as well, surveying these bubbles, and we can really see hundreds to thousands of these bubbles in the H1 distribution. Also, relatively early on, it became quite obvious that when comparing to traces of, for example, ionized gas, the ionized gas seems to sit within the centers of these bubbles, highlighting the connection between stellar feedback. So this is stellar feedback in the young stages and the later stages as well, in the supernovae, and the connection of those processes to the formation and evolution of the large-scale bubbles across these galaxies. And I'll talk a little bit more about that later in the talk as well. On the theory side, the implications for the evolution of the ISM and the involvement of bubbles was also recognized quite early on. So here we can see several examples from, for example, the very famous three-phase structure of the ISM and the involvement of supernova bubbles driving one of the phases of the ISM and the evolution of the different phases of the ISM across galaxies' importance. There was, for example, here up to kind of the mid-70s. So as well, this has been known for quite a long time here. So ultimately, bubbles really do constitute an important part of galaxies, an important part of the structure of galaxies, but an important part of the evolution of the ISM as well there. And of course, very recently, we've seen now very beautiful examples from the JWST covering these nearby galaxies and just the incredible structures that you're seeing here and the vast number of bubbles that we can see across these galaxies. Here, I'm just giving an example of around 6 of the galaxies. We can identify thousands of bubbles across these galaxies. So for example, here, I'm just showing the bubble distribution across NGC 628, where we identified 1,500 bubbles across these galaxies. And one bubble in particular that stood out in this galaxy and even across all the galaxies, I really don't think there's a bubble quite like this, and that's the phantom void bubble. So this is a bubble which is found again in the galaxy 628, or the phantom galaxy, which really stood out here in the JWST observations. This bubble is around a kiloparsec in size and extremely round in its morphology, which is really quite rare across these galaxies. We see typically the bubbles appear to be elongated and elliptical, but in this case, this is a very round bubble, which really makes it stand out. So the bubble is most evident in the PAH emission across these galaxies, which is why it really stands out in the JWST observation. So here you can see, again, that example of the bubble, but here just showing the JWST 7.7 micron emission. So this really picking out the PAH emission. And you can really see this large-scale structure, very spherical structure with the cavity within the center here, which is again around a kiloparsec in size. So as well as the PAH emission, which is really tracing the low surface density gas within the galaxy, we can also see this within the molecular gas, so the CO 2-to-1 emission, as seen by ALMA here. And we can see that the bubble as well, at least the bright rim of the bubble, the dense peaks around the bubble, so these molecular clouds. Here we're seeing slightly lower resolution, but you can still see the structure of the bubble traced along the edge here with the CO emission. And what we can do here is convert this to a molecular gas mass. We found that the bubble is also extremely massive. It's around 10 to the 7 solar masses in molecular gas mass. The atomic gas we see is around 10 to the 6 solar masses. So this is extremely massive in its both molecular gas and the atomic gas here, but molecular gas dominated. We also see significant ionized gas here. So here we can see observations from MUSE-H alpha. So this is from the VLT. And we can see that there's significant ionized gas distribution around the rim of the bubble. There's a low-level diffuse ionized gas component actually filling the center of the bubble as well. So there's significant ongoing, potentially star formation, potentially supernovae, but ultimately a lot of feedback is happening within this bubble, as seen by these very nice MUSE observations. As well as this, we can study the distribution of the stars. So here we have very high resolution, very deep HST observations covering all the way up to the near UV. The young stellar association from those HST observations. So this is the young clusters up to around 20 megayears in age here, which I'm highlighting as contours on this plot. And interestingly, we can see there's a lot of young clusters within this region. We're finding around 10 to the 5 solar masses of stars in young clusters less than 10 megayears across the bubble. And in particular, we're finding this distribution of potentially somewhat younger clusters distributed through the shell of the bubble compared to the center of the bubble, where the center of the bubble is more on the age of around 20 megayears. That's the structure of the bubble. We can also study as part of this work the kinematics of the bubble. So we have the molecular gas kinematics from the ALMA CO2 to 1. We have the atomic gas kinematics from the VLA H1. We also have the MUSE VLT ionized gas kinematics that we studied as part of this work. And we find that the expansion speed of the bubble is around 10 to 20 kilometers per second. This is a relatively fast, not extremely fast, but given the size scale is around a kiloparsec in size, this is still relatively fast expansion speed that we're finding across all of these traces, which appears to be relatively consistent. And of course, then we can calculate a total kinetic energy budget of the bubble as well, given the previous mass estimates. And we find that the total kinetic energy is around 10 to the 53 ergs, which is a lot of energy. Just for context, the typical supernovae injection energy is around 10 to the 51 erg. So this is a significant energy input if we were to drive this by a supernovae. As well as this, we made estimates of the expansion speed from various arguments for if shearing was to have a significant effect on the size scale of the bubble at the galactic centric distance of the bubble in the galaxy. If shear was influencing the bubble, it would become extremely elongated, but we're not seeing that. So essentially, how fast does the bubble have to expand to counteract this elongation effects? And again, we find in the range of around 20 kilometers per second, expansion speed is required to drive the expansion of the bubble before it would become extremely elongated on the time scale of a few tens of megayears, which we expect the age of the bubble to be, given those young clusters associated with the bubble. We compared the radial distribution of the various traces that we use to study the bubble. So with the JWST PAH emission, comparing that to the HST H alpha emission. So this is high resolution view compared to the MUSE. We have the HST UV filter, which really gives us the population of the young stellar clusters. We also have the ALMA CO2 to 1, which really gives us the molecular gas, and then the VLA H1, which really gives us the atomic gas. So we can compare the distributions from these, and that's what I'm showing here. And we're really seeing that the entire bubble is traced quite well with the molecular gas, and we can see how that peaks there in the red curve. We can see that the ionized gas and the dust really start to peak on the inner side of the bubble's edge. And as well with the UV, we can see the UV is slightly on the inner edge of the bubble. We can see that the kind of the inner shell of the bubble is really traced by those young stars. And overall, we see the H1 distribution. Again, this is somewhat lower resolution, so high resolution H1 atomic gas observations would help here, but we're seeing that there's this smooth curve across the bubble as well. We also looked at the distribution of the young stars and those young clusters, which I previously showed across the bubble. Here I'm showing those young stars on the y-axis is the age of the clusters. The size of the point is the mass of the cluster. And on the x-axis is the radius from the center of the bubble. And we can see some interesting trends here. For example, firstly, we're seeing that there's a significant population of relatively young, so less than 20 mega-year-old clusters, which are distributed through the center of the bubble. And interestingly, towards the shell of the bubble, we can see that there's a downturn where we can see very massive and also very young, so less than 10 mega-year-old clusters that are distributed on that inner edge of the shell of the bubble. So in all, we're seeing that this total mass of the stellar component within the bubble is around 10 to the 6. Around 80% of that is actually within the shell of the bubble, and only 20% is actually within the bubble itself. So how do we piece this all together? What does our understanding from these observations give us in terms of a scenario for creating such a striking, quite unique looking bubble? So what we think is happening is that, for example, as we're seeing here in the phantom void precursor, just to the north of the phantom void, the young stellar feedback, when the stars are initially forming, inject their winds, inject their radiation into their surrounding, and really cause the expansion of somewhat smaller scale bubbles, really seeding the evolution. You can see quite a few of these small scale bubbles in this image, but also across the galaxy, really driven by these young stars. So these stars which are 10 mega years and less, injecting their energy and momentum into their immediate surroundings, which is the dense molecular clouds where they're forming with it. After a few mega years, the very massive stars which have formed go supernovae, and that supernovae can then expand into the pre-processed lower density material, which is then resulting from that young feedback, and really expand and drive the expansion of a larger bubble, which then kind of supercharges the expansion. And then following that, we can have subsequent generations of star formation happening along the shell of this bubble. Here we can see that this is actually still ongoing within the phantom void. We know that there's hydrogen alpha, so we know that there's feedback happening. There know that there's young stars there in the rim of the bubble. So again, then these young stars, this next generation of stars, drives their young feedback, and again in their later stages of their life will again then go supernovae. And again, that process happens. Those supernovae can drive and supercharge the expansion of the bubble. And again, you get subsequent star formation, and the next generation then injects their feedback, goes supernovae, and then can expand the bubble even further. So essentially, we have this chain reaction of feedback, star formation, driving the bubble. And ultimately, this happens in this case, has happened on a very short time scale and allowed the bubble to grow into this spherical, really quite large scale striking feature within the galaxy without being ripped apart by the shear effects of the galaxy, which will happen, of course, as the bubble grows. These effects become more significant, and eventually the bubble will be sheared, elongated, and we'll end up with a bubble-like feature, potentially akin to one of these inter-Ram region bubbles, these large-scale bubbles that we're seeing quite often across these galaxies, not just here in NGC 628, but also within other galaxies as well. So we really think that this bubble is quite a unique feature just because of the way that star formation and feedback has really driven the bubble on a short time scale. We think that these kind of features are relatively rare within these galaxies. We're not finding many so far across the sample. We know that they most likely are there, and we are looking for them, and we expect that a handful will be found going forward. And that's where the future lies in understanding these large-scale features. But thank you very much for joining.